are solved games. So to understand what exactly is solved games.
Just to begin, can you tell us your class?
We are from first year. So what we'll be talking about is basically computational dynamics of how solved games work, how we can develop an algorithm to actually convert, let's say, NP hard problems, which we'll be discussing further, into sets of B groups. And basically, the question would be like already papers exist, what would we be contributing? So we know NP problems could be transformed into set of another NP problems, for example, famous 3-SAT problem, right? So what we're trying to evaluate, establish, or discuss in this problem is if we are able to make repetitive algorithms to determine solved games. Like, so what is solved games? We discussed that. So if we are able to determine them, probably in the future we could help understand the nature of NP problems further. So what is a game, right? So when we talk about game, you think you're going to play something, right? But in the real life, or let's say in the complexity of playing games is nothing but two players taking turns to do some decisive actions, which are not governed by the luck factor of, let's say, randomness, and their information that has been provided to them is absolute in the sense that no bias can exist, right? So when we talk about, let's say, why game theory plays a pivotal point in research. So once we're talking about, let's say, understanding mathematics, or let's say understanding economics, or let's say physics for that matter of fact, we need to understand that at the pivotal point exists the decision-making skills of why certain thing can happen, why certain thing can happen, why certain thing does not happen, right? So game theory helps us deduce in a sense that why mathematical models would work or would not work. For example, when we're talking about the Hilbert's, when we're talking about Goldhaus incompleteness theorem, it is in some way related to what game theory suggests in understanding the concept of how exactly algorithms could work. So my friend here would start with the first game that you played in your childhood, rock, paper, scissors, right?
So what are combinatorial games? So combinatorial games are those games which include two players, and they have perfect information of the game, and there are no chances for mechanism of randomization like to roll a die or to flip a coin. So it is completely based on the strategy of the person who is playing the game. And on the psychological analysis that you mentioned is that a group of researchers from the Chinese university have published a paper mentioning the role of psychology in winning or losing at rock, paper, scissors. What they did was they took 360 students, split them into 6 groups, and made them play 300 rounds of rock, paper, scissors. And they found out that winners tend to repeat their strategies, whereas the losers tend to shift their strategies. So the optimal game strategy would be that if you win, then don't repeat your strategies again and again. Instead, play the move that will beat your strategy, which had helped you beat the person. Or else you could play the move that the other person has played. And the probabilistic distribution, as there is no bias in the game, as every move has 1/3 probability, and it is based on luck, as the first 2 moves are basically random. So an analysis of the first 2 moves are necessary in order to strategize the move.
Alright, so as you can see, right, you're probably thinking what a trap it is, no? Any point you want to move on, right, we're going to lose. So that is essentially an example of solved games. So solved games basically have an optimal strategy to play. Now, let's say you want to win in this game, it's not possible, right? But we can determine something known as a state sample size. So what would be my optimal move to get into a condition of Nash equilibrium, so that an eventual analysis of where the both groups win, that is getting a tie in this, for matter of fact, can go, and we could also determine the game tree complexity in this. So basically, what is game tree complexity? Right. So state sample size. What would be my first move? Right. What would be my first state from where I start? The state sample size would be any of these 3 probably if you want to win, right? An optimal game strategy. Now, if you can see, some parts have got lesser number of complexity into them compared to others. So when the leaf nodes diverge into a sense of different algorithms that will lead to different results, it leads to the development of game tree complexity. And higher it is, the higher the computation power required to figure out the theorem is. Also talking about the first player bias, right? You could see there are around 3 lakh or 2,50,000 moves that can be possible in game of tic-tac-toe where the code is such minuscule. But yet you see that a first player bias is starting from the top is the first player and bottom is the second player. You could see the green wins in terms of how much you can win. Let's say the third or fourth move is way higher than you can move in the win in the later moves. Compared to that, you also see a lot of yellow dots, right? So those points are the optimal Nash criteria of where these games could exist. So why this is important, we'll discuss in the NP hardness. But it's important to know the game of name first, a mathematical miracle.
So the name game. It is an impartial game as both the players get the equal number of moves. And what are P and M positions? P positions are the winning positions for the previous player who has already moved who has already played the move. And N positions are the winning positions for the player who is going to play the next move. So the optimal game strategy in this case would be that.
So, in an optimal game strategy, you would probably want to make the min sum equal, which is the mathematical equivalent of, to actually evaluate how the different chances could be, and taking the first player bias into consideration. You could explain non-match today. Yeah. So, talking about mini-max and max mini, right? There are two concepts that are used heavily in game theory. Is in a sense, like, let me give you an example, right? All of us go outside, let's say 8 pani puri, right? We want to get as much as amount you can get in 10 rupees, right? So you're optimizing in a sense that you pay less but you want to get more. Max mini, right? Other cases of scenario, you'll be like, you go to a very high-fi shop, you'll be like, I'll buy this thing, coffee, Starbucks for 500 rupees. You're paying more, you're getting less. So optimizing that, you understand the actual algorithm and the use of use case of this. So coming to the NP hardness, right? So the entire focus of this paper is to understand how transformation of NP problems could be done into P problems. So classifying them very simply, P is problems that could be solved in polynomial amount of time. Let's say bracket 2 plus 2 minus 2 is a very simple P problem. But let's say if you are first grade, you don't know how what mass works. So what we will do is we'll add 2 plus 2 first and then subtract 2 from it. What we have done is classified an NP problem in essence which would take you, let's say, 2 hours of your period, done it in 2 minutes. So that is what we are trying to do. We are also trying to understand the skill-based incentive in this. Like for example, I'll give you a simple. You might have heard that chess is an NP hard game, right? You cannot figure out the exact number of optimal position that would be played for a substance because 64, right? So if you think of it in this way, 64 squares in a chessboard, right? 16, 16 each side. Total, if you just estimate, let's say how much each piece can move, it would be 64, let's say to the power of 16, that goes beyond well the amount of time that something would be done. I'm just talking about the initial moves, right? But if you break it down into sets of 3 problems, like our analysis of 3000 games that we picked up from chess.com. So you see, first move played by white is the e4 king's pawn. Right. So you would think, alright, the pawn move has been played, right? So the white player takes the first move in chess, right? So we see that over a period of time, the most probable move that has been done is the e4 king's pawn. Now the question comes, how do we determine what is the optimal strategy to it? It's not by treating chess as an NP hard problem. We break it down in sense of little p problems. What would be the optimal move to that possible move? As you can see, players often do the e4, e5 opening game towards that problem. So what we're trying to propose is, if you look like this way, with the mathematical model of how knight moves throughout the board, it does look random, but again, it's set of just observing at the knight, so you can estimate how that works. So here comes the part. So you must like, of course, you're gonna play Super Mario, right? So group of researchers were talking about this problem. This is the infamous 3-sat NP hard problem. And the problem with this is, like, if you notice here, there are a set of variables that the start player has to go through. The function goes through this variable, has to deal with x or x naught, y naught, z naught. Completing this chain, it checks in at the cross space. So imagine a function, right? So function checks in the cross space. If the value has been determined for all of these clauses, then only the function can calculate. Like for example, I'll give you a problem of example of NP hard problem. The Riemann conjecture, the Riemann hypothesis, is a set of NP hard problems, right? But still we can figure out the zero of it. Why is that? Because we take initial conditions, let's say talking about one variable and one clause, and then convert it. So that is what scientists have tried to do. So this is the same problem converted into a Mario game. This is still the NP hard problem. It's mathematical reason for why you lose this game. But in essence, you can now visualize this problem instead of looking at flowcharts and graphs. So this is the need. We need to change the outlook for how exactly we look at games. We need to change how the outlook of solved games would exist. We need to change how logic works in sense of visual and comparative measures. So that is what we are trying to propose. If we could break down sets of problems into smaller sets of subsets, in sense where there is solvability in p exponential time, we would also prove their solvability in, let's say, NP space or other exponential complex spaces and complexity. So guys, you must play Sudoku, right? You're genius, right? So it's easy to play 8 by 8 Sudoku, right? But not 19 by 19. So computers can't do that too. So if you can play 19 by 19 Sudoku and tell the computer how to do it quickly. Probably you can solve cancer, cure the cancer or global economy, who knows? So it is important to play games, so keep on playing games. So as Scott Anderson said,
If P equals to NP, the world would be a different place. Everyone who could appreciate symphony would be Mozart. Everyone who could follow a step-by-step argument would be Gauss. Everyone who could recognize the good investment strategy would be Warren Buffett.
so simplicity is the final achievement. After one has played a vast quantity of notes and more notes, it is simplicity that emerges as the crowning reward of art, like shopping. So I encourage all of you to play lots of Sudoku, lots of sort games. So in the future, maybe we get to cure for cancer from playing Sudoku. Thank you everyone.
So in this you're talking about game theory and you have applied it to games. So what are the best tools of game?
Ma'am, it's very vast field, right? Like talking just about Nash equilibrium. Nash equilibrium is an economical concept, right? In real world scenarios. But what we wanted to propose was that not just game theory itself. See, tic-tac-toe is easier to explain rather than like if I got like stock trading or how market works in aspect. So that is why we chose it. But it could be used in market tradings, mergers, let's say even economical transactions, global economy, fuel rate manipulation, even economy variation between dollar and yen rupee is a concept of that because everyone needs to be in profit.
Have you heard about prisoners?
Yeah.
So how would you predict the behavior of unicorns or the game?
The issue with prisoner's dilemma is in a sense paradox. Everyone loses something, right? So it's one example of Nash equilibrium where the eventual good is to minimize the loss, which we explained in the concept of minimax, right? So in a sense, there would be no actual work that could be done to minimize the loss more than that, but we would predict that at the best case scenario it would be to equalize the loss at least at these cases.
Okay, Lakshman, very energetic presentation.
Thank you.
So, one thing, what are the deciding factor which why the system, so even all the two-player game system move towards the next equilibrium? Let me complete. Is it due to some psychological factor or is it due to the lack of information?
Right. So we discussed two of those, right? So in the rock paper scissors, for example, if we go there, right? So there we talked about like first player bias. If you have a look at that, these are individual probabilities of where the player would do. This is like probability of paper, scissors, and rock. Right. So if you look out, they equalize over a time period, right? So in the nature, certainly in every empirical aspect, we cannot overlook psychological analysis at that point. But let's say for deciding games like tic-tac-toe, there exists a first player move bias. But there exists a first player move bias. Maybe we were playing game yesterday, it was very evident why someone was winning, by someone's losing. So the issue with game theory is in a sense that you have to know the bias in first hand because then only it will be a sort of thing. So perfect information needs to be present. So that is what we think. Those would be the deciding factors in
And like we have asked about the prisoner's dilemma. In the prisoner's dilemma, it's going to be more related to the psychological factor, or it's the lack of information that you are not knowing about the action by the other person.
So when you talk about like of course mathematics though is a grounded reality, right? It's very hard to equate numbers with sense of emotions. So once we're talking about game theory, we need to understand though its application is numerical, but it's being used in real life scenario. So probably any amount of connection is built between these two so the probabilistic effect of both of them choosing the best option would be higher even when the lack of emotion is not present because it is people we are talking about, not let's say upon theorems or certain things like that.
Last thing, just to in the realistic system, when we do talk about the realistic system, then would it be a better choice to go according to the game theory completely because in real system a lot of other biases do exist, emotional or you can talk about multiple other factors.
Right.
So how much do you think in the real world game theory is realistic?
I think game theory is something that equalizes loss. I'll give you a certain example. Recently an action was done by our military where some casualties were done. So the problem was what could have been done, what could have been not, what could have been done. I mean, that is the point. Game theory minimizes loss in a sense. So of course biases exist, but again this is not real people we are talking about. We're talking about solving something that most common person would not feel in essence.
So does game theory have
Yeah, I usually working on a mathematical paper that could predict the flow of the Navier-Stokes equation, because we could just analyze. So, if Navier-Stokes equation, right, has a starting point and initial condition, so the flow of it is determined in a sense. So, if you could determine the flow of a function, right, like we talked about, if you could determine flow of a function, then transform it into, let's say, a solvable problem, like we did for the chess problem, right, or for the 3-SAT problem. We transform that into something that is visually applicable and understood. Probably it's easier to understand or acknowledge Navier-Stokes equation rather than a bunch of numbers that could practically be used.
So they have already been used.
Not yet.
So we were talking about Navier-Stokes.
Right.
There it has been used, but
Not yet. It's proposed. It's an individual paper that.
So you talk about minimax algorithm.
Yeah.
So they want to do more one view. You know about that? If anything can go wrong, it will go wrong.
Yeah. Right.
Okay. So my question is, so if you go about that route, that minimax algorithm will be more easy.
Yeah.
But if you see the statistics that say more than minimax, the maximum algorithm will do. Then why?
Alright, so minimax is about, like when you talk about minimax, we are talking about minimizing the loss in a sense. So even if anything goes wrong, how to prevent it to a least amount of degree. Like for example, people say don't try or spill milk, but if you can scoop up the milk fast and serve it back, it is better than spilling entire liter of milk, right? So when you're talking about Murphy's law, we're talking about a deterministic factor, right? That something will go wrong, it will go wrong. That's a statement that is completely coherent to minimax. Because minimax is treating, alright, if something has gone wrong, how are you going to get emerged from it? Let's say if my calculation has gone wrong, right? How am I going to go back? Am I going to start this sum entirely again, or I could just see what step I have done the mistake, right? So that is why, and even if you're talking upon statistical measures, right? The bell curve, the probabilistic distribution overall, like eventually would reach a position where it would be neutral for losses and profits in an essence if it's statistically talking.
Okay. And one more question. So about chess. So you know chess is perfectly?
I am pretty sure a perfect game of chess is very hard to compute in a sense.
So there is one more game like chess is flat. That is perfect game. But if it is only perfect, then there is 2%.
Yeah.
But when more than 2% game, that perfectly has been more. And for the most of the game, perfectly has been more when the number is 0 to 3 or to 4. Then why?
So that also happens in real life scenario. When we talk about game theory, we talk about players. There are two people also, right? We know if two people love each other, third one comes is going to make a mess, right? So in any real world scenario that happens. But statistically speaking, the perfect way to expand game theory would be solving bits of problem where it exists. Like for example, checkers, right? Chinese checkers is a 4-player game, but it has also been solved mathematically. So how it was solved was it was taken as an individual reference was 64 checkers. What it was done was 2-player game and converted into a set of T problems and then solved for Chinese checker also. There are already been solved for 5 people, I believe it could be done for me.
But if you see it, if they keep the person, then instead of going there, then going back now. If you don't begin by the then you must sacrifice by them, but you haven't. What is the main reason that even after making Chinese, you can't get it?
I'm sorry, even after?
Making Chinese, like they get by now.
Right.
They is Chinese also. When they agree person, what they do, they go backward. And suppose if winning point is 100, they are 100, then they will make Chinese match. So even after winning those Chinese match, no one can get a perfect answer. So what is the reason?
I mean, the point we are talking about is the trinary already is a perfect answer because it's a stalemate. So stalemate is already a match equilibrium state we're talking about in game theories. But conversion to win optimal strategy in trinary is a class of problem called the EXP problem. So actually calculating sets of various probable kinds that are going to reach into sets is it's hard to compute, right? So that is the probable reason. Other than that, I have not studied much in trinary.
This actually, when it is calculated,
Right.
then after 3 points, the move of the third person portion at the next fifth move of the first person.
Right.
So they diagonal map in the Chinese map. That's how it's good.
Right.
By the way, inaccurate.
Thank you so much.
Thank you very much. So we are still having that time constraint, so please take care of that. And so sorry about that, we cannot take the questions from the audience, so you can still message to that number if you have any queries. Next presenters would be Hari Prasad, Vedant and Sandra from St. Stephen's College. They would be presenting on diagnosing neurological or psychiatric disorders from electroencephalogram data using features of nonlinear analysis and neural networks.
Don't step on that. I think
Good afternoon, everyone. So today we will be presenting our study that we conducted on diagnosing neurological strategies of
This title the one of the
everyone. So today we'll be presenting our study that we have conducted on diagnosing neurological / psychiatric disorders from EEG data, or commonly known as electroencephalogram data, using features of nonlinear dynamic analysis and neural classifiers. Okay. So first of all, before moving into the presentation, I would like to mention that part of this presentation is completely novel. So we will only give an overview of what we have done because we won't completely diverge into the details of what we have done because it's completely novel and new. Okay. So let's start with what an electroencephalography is, or abbreviated as EEG. Electroencephalography is a technique to map out electrical signals from different parts of your brain. So basically, if this is your brain, these are like electrode placement. This is called a 10-20 placement system. So electrical signals are acquired from all these probes and then mapped into a system. So basically, every electrode is a differential amplifier. So it maps out two difference in the voltage signals in two different parts of the brain, and then we can get a data set of all the electrical behavior of the brain. Okay. Now, considering now we know what EEG is, now I'll talk about what an epilepsy is. Epilepsy is a disorder that happens because of many reasons, maybe genetic, hereditary, or can be caused due to external trauma. Epilepsy usually happens with many convulsions. The patient undergoes many convulsions or seizures, and then they will have sturdy muscular movement. And all these involve a lot of muscular movement. So that's one thing that I would like to mention. So as you can see, this is an EEG, a typical EEG, and you can see these sparks. These are called Bell phenomena. When your eyes move, this creates a lot of impact in your EEG. It's a lot of disturbance in your EEG. So extracting these features, extracting brain features, extracting neurological features from an EEG is basically considered a problem or a still developing task which involves to reduce these biological artifacts. So now, what we have done, our method of analysis include these steps. So first, we obtain a data set that have epileptic and non-epileptic behavior, electroencephalogram behavior. Then we denoise the data using something called a TQWT. Then we extract the statistical and nonlinear features in the data, and then we apply a classifier, specifically KNN, three classifiers, KNN, SPM, and random forest classifier. Then we discuss our results. So let me give you an overview of the data set that we have used. We have used the well-established data set provided by Bonn University of Germany, which includes, this is the description of the data set, where like set A to E contains, set A and B contains normal brain activity, set C and D contains seizure-free but pre-ictal activity. So ictal means seizure. So pre-ictal means the brain before seizure. So these contains pre-ictal activity, and set E only contains seizure activity. This is obtained from 5 different subjects. And now, what are we going to do? So this is like a normal samples of these EEG samples from all the data sets. Now, what are the first thing, since we are doing a non-linear analysis on it, basically a chaos study on it, so first we need to denoise the data. So we will use a modified form of wavelet transform. This is a recently developed tunable Q-wavelet transform. So we use this and we kind of decompose our signals into multiple bands, and then we use an inverse of the same method to denoise the data, to reduce the random noise of the data, that we feed in to extract our features. Now, this is a slightly example of why we use TQWT. So, in the first, this is a Lyapunov leak map, and like this is of the before denoising the data, and this is after denoising the data. So you can see because of the activity due to random noise is less in the next heat map, in the heat map at the right side. Okay.
So the features that you have to extract should have significant difference between the epileptic data versus the non-epileptic. So, for example, in this diagnostic features that we use, you can see that in the mean, when we're calculating the mean, so the x-axis is the data, the set of data, and from the point 200 to 200 data, we have epileptic data. So you see that there's not a lot of difference before the 200 data set and the beyond 200 data set. You see that the mean doesn't really show a stark difference. But then if I use something like a standard deviation or kurtosis or skewness, you see that there's a very stark difference between second epilator, which is beyond budget, and non-epileptic data. So these are the features that we can use. I will go into the non-media features, non-media features. In this one, I wish I could explain it more, but in different time constraints, I'll go into like a little bit. So the first feature that we use is the real-world experiment. So the real-world experiment shows the chaotic nature of the system. So if how sensitive it is to the initial conditions. So if the real-world experiment, that is the lambda factor there, if it's positive, that means the system is chaotic. So we calculate the real-world experiment of the data. Another thing that we can calculate is the first experiment. So the first experiment shows how deterministic your system is. That means just how much memory the system has. For example, if the first experiment is 0.5, then it would represent a random walk. So if it's a random walk, then it has no memory of the previous step, and it has no memory of the previous step. But if your first experiment is greater than 0.5 to 1, as it increases, it becomes more and more deterministic, and it depends on the previous value. It depends more on the previous value. So you can see that the function tends to become a more monotonic function. On the other hand, if h is less than 0.5, then it becomes a mean recurrent function. Again, it is unpredictable, and it tends to, just because you have a high value, you cannot predict the next value that comes. It will be a low value. So the other feature that we could study is the sample entropy. So sample entropy will tell you how much the time series, the data repeats. So entropy is basically information. It depends on the topic of information and entropy. So the more that you can compress the series while conserving the amount of information, that shows you the amount of entropy resistance. For example, the first series over there, if you calculate the mean of the series, it would be the same, but then you know that the two series are completely different. So in A, for example, I can compress the series by saying that 0, 1 repeated 10 times, for example. So I get the same amount of information by compressing it, but I can't do the same for B. So I would say that B has more information than A does. The next thing is dependent fluctuation analysis. So dependent fluctuation analysis tells you the self-affine nature or the fractal nature of the time series. So basically, if you look at a short period of time and the statistical features of that, how much does that represent the overall a larger time series? How much will you look at the small series and predict the statistical features of the larger of the rest of the series? So over here again you see that the real-world experiment doesn't really tell us much, but the first experiment you can see that after the non-seizure period, you can see that it is above 0.5, so it is slightly deterministic, and then it oscillates slightly. The sample entropy, you can see that the entropy actually decreases when during seizures, and you can see that DFA also again after the 200 points, you can see that it widens the difference. So these three are features that we use.
So now once we actually have classification features, we need to do actual classification. And the way we do that is we have three methods. One is the random forest, we have the k-nearest neighbors, and the support vector machines. And all three are different features, and the random forest is essentially based on a method called decision trees. So I won't go into what decision trees do, but they are independent classifiers. Each decision tree classifies a set number of data and features. A random forest takes a large number of decision trees which are all uncorrelated. And the way it maintains uncorrelation is it gives each decision tree randomly samples from the data set and also randomly samples some of the features. The fact that they're all uncorrelated gives you sort of a set of independent observations of the classification. You take a majority, and that gives you your actual classification. The k-nearest neighbor in STM are very similar. What we do here is each data point is mapped into a space of the features. So it's a space where each axis represents the feature. And what we do is we map a new data. So in KNN, we map a new data point in that space, and we see what are the nearest neighbors to that data point. And whichever category there are more closer neighbors to, we assign the new data point to that category. In SVM, we look for a plane, a hyperplane that can separate these two data points best. So if the data set is completely linearly separable, that means you can find a plane that completely separates them and gives them 100% accuracy. This is our data mapped into space. It's a 4-dimensional space, so we've taken A6 plots which combine each of them.
But I think it's better to look over here. We removed over here basically the lecture where we removed the mean and Lyapunov exponent. So mean from the statistical and Lyapunov from this. And the reason we did that is because they didn't really give a lot of information. And here we can see a clear separability, a plane that can separate the blue and the red, and here as well. These are our results for statistical features for random forest. We get a 99% accuracy, 98.3, 97.7. For non-linear dynamics feature, we split our data into two sets, training and testing. And for testing accuracy, Indian and essay we got 100% accuracy, which means the data is completely acceptable. And for testing, we got 89% and 91%. These are just the number of nearest neighbors we took for the statistical and technical features.
Okay, now I will talk about the novel method that we have developed. So, as per we know, like we have developed some heat maps while researching, while studying electroencephalography. So, this is a heat map that mapped into like this is a Lyapunov heat map and interpolated a map into like specific electrodes or electrode placement of the brain. And now, so we can see like you can see the difference between a normal and a schizophrenia. Schizophrenia is a psychiatric disorder. So schizophrenic and normal brain subject. So this difference is not apparent in a simple EEG. So what we are doing is, so we taken this data from the MD numbers of schizophrenia data set, and then we use a convolutional neural network to classify the subtle differences in schizophrenic brain activity and normal brain activity. So the actual implications of this is, so you can see our accuracy, final accuracy was 76%, which is not that great, but the thing is, depending on our data limitations, this is the maximum that we have developed. So the best part or like the interesting part about the study is, so we have like since the schizophrenia data is very much harder to separate from the normal brain data, this can be built to study ADHD and multiple other brain disorders. So with that we conclude our presentation. So thank you.
Hari, Vedant and Sandra, but just tell me a few things. What is your input data? Is it the muscular motion of the eye, or what is the real data?
So yeah,
muscular motion.
No. So like the bond data set that we have, it contains a lot of data which which just maps brain activity. So what we have is it contains all of the data. So what we do is we directly treat. So we have a set of non-epileptic and epileptic data. So we kind of make into two different classes. So let's see, epileptic is 1 and non-epileptic is 0, and then we feed into the classifier. So the thing is, like even the denoising step won't actually do much for the muscular artifacts or biological artifacts that I mentioned, like the eye movement or muscular movement. So yeah,
That's all. Okay, so by using the classifiers, you are deciding whether a given data, whether it will show you that features or not, and on the basis of that, one can take
the chaos of the feature determines whether it will be a
Yes. So now you are using something called k nearest neighbor method.
Yes.
So for the k nearest method, every time to fit the data, we require the information about something called we do cross validation to decide on how many neighbors we do require to fit. So what method of cross validation are
So
you?
we didn't actually perform cross validation for KNN because we chose the k nearest neighbors manually. We did not take a method to choose what case value would be, because our actually aim, what method we wanted to use was support vector machines. Because that was sort of the aim. The k nearest neighbors was the preliminary step to using
In
support vector.
KNN, accurate choice of that particular
I know,
parameter is very much.
yes, I know that. It's just we weren't focusing on it.
In your novel part, you are talking about the neural network. And for the statistical result, when you are talking about accuracy to be 100%, what does it actually mean?
Okay, so in the testing data, what it means is that, supposedly for the SVM, what it means is that when you map this into your parameter space, then you could find a hyperplane that completely separated the two data points. So you could divide the space into two regions, where all the epileptic points were in one region, all the other were in another region. You found a hyperplane set.
So in this you're using convolution neural network.
Yes.
yeah, we have so convolution neural network is a very like it's only used in image processing, and it's more used in image processing because we have heat maps we are feeding it. But generally, like convolution, so we have like multiple other simplest kind is NLP, multi-layer perceptron feed-forward network. It's a normal network which feeds in single vectors, single data vectors inside. But in a convolutional network is much more advanced. It uses tensors as a input, so multi-dimensional spatial features it can map out. There are other networks we have. There's like networks called LSTMs, long short-term memory networks, and there are multiple other classes.
And you also refer to T.
Yes, T-level Q-barrier transfer. So it's a new, recently developed method to basically decompose the signal. So let's say, so Fourier transform, everyone knows Fourier transform. So Fourier transform actually has some limitations in it. It has very low, the problem is we have a very complicated signal. Sine and cosine cannot be different, used to differentiate. So for example, if we like a biological signal like EEG has very complicated waveforms inside it. So instead of using a predefined function like sine or cos, we use something called a wavelet. Wavelet is a short, discrete form of a wave that we use to map out. We scale the wave to entire time series. Then we figure out the frequency, we kind of decompose into frequency bands like this. So and then so what we are employed here is we decompose everything. So the noise will be reduced. So we decompose everything. Then we do the inverse of this. So then we get a noiseless data, much more noiseless data.
Okay. So you talked about that optimum plane that divides. So how do you decide upon how do you get that optimum?
So that we can convert this to an optimization problem. The way we do that is we measure distances. So data points can be given two categories, one is +1, one is -1, and we define a function like this, w star x minus b is equal to 1 or w star x minus b equals -1. We're looking for two planes and you're going to have a hyperplane that best separates them. And what we want to do is we want to maximize the distance of the nearest points from that hyperplane. And what we do is we find that this distance is actually 2 by the mod of this parameter omega, and this converts it to a minimization problem where we minimize omega. And by minimizing omega, we can maximize this distance and find the best hyperplane.
And has this process been used in the treatment of psychiatric disorders?
No, not for psychiatric. Psychiatric disorders using neural networks, using specific, because we didn't use it for psychiatric disorders. Yes, this method was used for epilepsy, which is a neurological disorder.
Yes,
It has been used, but the paper that we referred to, which used this, we got a better accuracy than they did in our result because we used this new method of noise filtering, the neural fluid.
So, but the other method has it been practically used?
It has been used. They have a specific accuracy. I don't remember what accuracy they were.
So in the papers that use this, what they do is they never employ this neural fluid transfer. And then they generally do this diagonal decomposition using something called discrete Taylor transform. Discrete Taylor transform has a limited Q value. So this Q is what we're doing. So what Q is a ratio between the central frequency and the time series data. So in a normal discrete Taylor transform, what they're doing is that this Q value is set. You can't change it. It's √2. It's set. But in tunable Q-Taylor transform, we can change it, which basically gives us a better control over the data, decomposing the data, so which gives us much better classification. And that's why a support vector machines or any other classifier works better.
So it has been used, but we get better accuracy than they got.
Okay, so EQWB.
Huh?
EQWB.
Yes.
There are two things EQWB. One is instability and one is invariance. So what is the difference between these two things? Invariance and stability.
Invariance so basically it does a multi-resolution analysis MRA, right? So basically we have a spatial and temporal okay, next one. So let's say we have a spatial and temporal resolution that we have, and for example, if we decompose our signal into multiple spatial and temporal forms, the resolution of the data kind of diminishes. That's the problem with any of the Fourier transform, SPFT, all that things. But in using tunable Fourier transform, any other Taylor transform, not even tunable Fourier transform, but even continuous or DWTs or discrete Taylor transforms, the good thing about it, even at higher frequency, you are getting a very good time temporal resolution. So that's basically is related to
You gave me about T2WT, but I'm asking very sure T2WT has two terms. One is instability of T2WT and one is invariance of T2WT. So what is the difference between these two things?
basically, the noising, denoising is what we have done. Is just, so we tried all this, and this is just a kind of unexpected method that we use. So since there was no, documentation that we could find on data recoverability, the TQWT is very less studied actually. It's a completely new method by Selensky et al. So it's very less studied method. Yeah, so we are thinking of studying a lot more about this.
So are you using XDC?
Yes,
Yeah. But then if you use Python now?
Yeah, Python.
Python have a gradient and
NNE.
yeah, which is particular for which is glory. Which is particular for which is glory. For that, yeah, and then is there library. Which is particular for which is glory.
Like frequency, like
For that, BM study and then EEG.
yeah, so that's what I say. MNE. That's MNE.
MNE, yeah.
So MNE, we used MNE to actually extract the statistical features. So that's why we implemented the sklearn pipeline. So we created the pipeline, and then with the actually the features were implemented using the MNE package only. The other feature packages we couldn't implement on the pipeline because the problem was it was our built-in frequency extractor, chaotic feature extractor. So we had to build like a multi-output classifier, multi-dimensional output classifier for this one.
So you in the what do you have
So the thing is, actually I won't go too deep into this because we are going to publish this work. So yeah, this work, this actually is a diagram map.
Yeah, more than 1 year.
Yeah. So the thing is, epilepsy data is always chaotic. We can only compare the chaotic. Actually, brain data is always chaotic.
Yeah, it's always in the level.
Yeah, it's always data level.
Never always in the level.
Yeah. Thank you.
Thank you very much, Vedant, Hari and Sandra. So with that, we come to the end of the offline part of the Meera Memorial Presentation Competition 2022. We'll have a 10-minute break. You can collect your refreshments and please join us on the link that's been sent to the group. We hope to see you for the online part that will carry on for today and tomorrow. Thank you.